Alright, now in this section we're going to be looking at a non-parametric procedure that is used to compare the locations of two distributions using independent samples. If you think back to the last module that we just got finished with, we looked at a procedure for comparing two populations using dependent or paired samples. But in this module, we're going to be looking at situations where the samples from different populations are independent. Now, the test that we're going to be looking at does not specify an inference about any particular parameter of location, such as the median or the mean of the population. The test that we're going to use is based on the ranks of the observations, and these ranks can either be assigned directly by the rater, or they can be based on quantitative data. So, for example, we could have a response variable that we're measuring on experimental units that is quantitative in nature, and then we could rank that quantitative data and use that rank data for this test. As an alternative, we could have a situation where one or more raters are actually ranking subjects or experimental units based on relevant criteria in that situation. And so we don't actually have a quantitative measure to start with, we actually have the ranks as provided by the raters. Now, the null hypothesis for this test is going to be that the two populations are the same. And we're really not talking just about the location, we're assuming that they're the same in every possible way. The alternative is either that the populations are different in terms of location with no particular direction specified. So this would be analogous to or considered to be a two-sided test from what we've seen before. Or it could be that the alternative is that one population is situated or shifted with respect to the other population in a particular specified direction. So, for example, the alternative could be that one population is shifted towards larger values from the other population, or the other way, we could have the alternative hypothesis being that the population is shifted towards smaller values than the other population. But remember that when we're talking about a shift, we're not talking about that in terms of any particular measure of location. It's just spoken of generically as some kind of a shift. The test that we're going to be looking at goes by various names, actually. We're going to call it the Mann-Whitney test. That's kind of the standard name for this test. It's also called the Wilcoxon rank sum test. And some folks will, in order to give everybody credit that came up with this, they may call it the Mann-Whitney-Wilcoxon test. So it has these various names. Don't confuse the Wilcoxon rank sum test, or this Mann-Whitney test, with the test that we looked at back in Module 2 for comparing two populations using paired samples. That test was called the Wilcoxon signed rank test. So this is a different test. Wilcoxon came up with these two different tests. This one is called the Wilcoxon rank sum test, and it's used for comparing two populations using independent samples. Probably the more commonly used name is the Mann-Whitney test, however. Now, the description of this test and how to perform it is somewhat involved. It is perhaps a little more involved than we had with the Wilcoxon signed rank test back in Module 2. And in order to describe this test in a way that makes it fairly easy to understand how to go about doing it, and also once we get into the actual computations to help us keep track of what's going on, we're going to have to define several pieces of terminology and notation. Or another way to say that, we're going to have to come up with some labels for the populations and the samples that we are utilizing. So let's talk about the populations and the data, populations and the samples from those populations. And we're going to talk about what I'll describe as a preliminary labeling and a notation. So there are two populations under consideration. And for our preliminary labeling, we're going to call those populations A and population B. So we select a random sample from each population. And remember that the two samples are drawn independently of one another. This is not a paired sample situation. These two samples are independent from each other. Now, we need to give a name or attach a label to these two samples. So since we're using the labels population A and population B for the two populations, let's refer to these samples as sample A and sample B. So sample A will be the name of or the label we attach to the sample from population A. And sample B will be the label that we attach to the sample from population B. All right, then we have to have some notation for the sample sizes. And so let's denote the size of sample A by n sub A, and let's denote the size of sample B by n sub B. We're going to start describing the process by which we analyze the data. One step in the analysis is to combine the two samples together, and then ranks are assigned to those combined observations. And we do this by creating an ascending data array from the combined sample. The observations are then assigned a rank that is equal to their position in the data array. So we're not going to sort the two samples separately. We're going to take the two samples, sample A and sample B, put them all together into a combined sample, and then we create an ascending data array for that combined sample, and then we rank the observations within that combined sample. Now, there's always the possibility of having ties, having two or more observations with the same numeric value. And so if that's the case, we have to come up with some way to handle that in terms of ranking those values. And so if that occurs, then to those tied observations, a rank is assigned that is equal to the arithmetic mean of the positions they hold in the ascending data array. So that part of this should be familiar to us. I think we had at least one example of that when we looked at the Wilcoxon signed rank test. All right, so we do combine the samples together to get that ranking, but we don't lose the distinction between the samples because we keep track of which sample each observation comes from. Is it from sample A or sample B? So once we have come up with the ranks from the combined sample, then we can think about separating those ranks into the corresponding ranked samples, and then we're going to sum up the ranks within each sample. So we'll denote by T sub A the sum of the ranks of sample A. We'll denote by T sub B the sum of the ranks of sample B. Now, associated with each of these two rank sums, okay, so T sub A is the rank sum for sample A, T sub B is the rank sum for sample B. Associated with each of these two rank sums is the conjugate of that rank sum. And the conjugate is denoted by putting, you can see that little tick mark or apostrophe up there in the subscript. So T prime A is the conjugate of T sub A, and it's calculated in the following way. We take the size of sample A times the sum of these quantities, so the size of sample A plus the size of sample B plus 1. All right, we take that product, and then from that we subtract the rank sum of sample A. And that's going to give us the conjugate of T sub A, which is T prime of A. All right, the conjugate of T sub B, T prime sub B, is computed in an analogous fashion, but notice we've got the sample size for sample B out here in front. So n sub B times the quantity n sub A plus n sub B plus 1. And then from that product we subtract T sub B, and that gives us what's called the conjugate of T sub B. Okay, so again, we're looking at the preliminary labeling and the notation for the populations, samples, and some summary statistics computed from those samples. Now, in order to facilitate the analysis, we're going to need another set of labels that we use in the analysis itself. So in addition to the preliminary labeling as populations A and B, with the corresponding samples A and B, we will need to establish an additional set of labels for analysis purposes. These additional labels will be populations 1 and 2 with corresponding samples 1 and 2 respectively. Don't get the impression that population 1 always corresponds to population A and population 2 always corresponds to population B. That's not going to be the case. The labels 1 and 2, these labels are based on the relative sample sizes. And how we make this association is shown on the next two slides. If n sub A is less than or equal to n sub B, then sample 1 is going to correspond to sample A, and sample 2 will correspond to sample B. Also, population 1 will correspond to population A, and population 2 will correspond to population B. Then we'll need some notation for the summary statistics for the two samples using this new labeling. And so n sub 1 will be n sub A, n sub 2 will be n sub B. The rank sum for sample 1, T1, will be equal to T sub A, T2 will be equal to T sub B, and then T1 prime, the conjugate of T1, will be equal to T prime A, the conjugate of T sub A, And T2 prime, the conjugate of T2, will be equal to T prime B, the conjugate of T sub B. So this is how these are associated when the size of sample A, n sub A, is less than or equal to n sub B, the size of sample B. On the other hand, if n sub A is greater than n sub B, then sample 1 is going to be sample B, and population 1 is going to be population B. And then sample 2 will be sample A, and population 2 will be population A. All right, and then we have the corresponding summary statistics down here. N sub 1 will be n sub B, n sub 2 will be n sub A, the rank sum for sample 1 will be T sub B, the rank sum for sample B, the rank sum for sample 2, T sub 2, will be the rank sum for sample A, T sub A. The conjugate of T1, so T1 prime, will be equal to T prime B, the conjugate of T sub B, and the conjugate of T2 prime will be equal to TA prime, the conjugate of TA. So you can see here, the easy way to think about this is that the 1 label goes with the smaller sample. And then from that, we attach the appropriate label to the population and to the summary statistics. I know you're asking yourself, why in the world are we doing all of this? You've probably never seen this kind of a labeling, this dual labeling, on any other procedure that you've ever seen before. So the rationale for this additional analysis labeling is driven by the structure of the Mann-Whitney table that we will be using to look up critical points. In order to do this test efficiently, fairly quickly, and without making errors that might occur if we had to construct the sampling distribution of the test statistic, we're going to use tables. So if you think back to really every test that you've performed, you've used some kind of a distributional table, a reference table. For example, you've used the standard normal table to test hypotheses about z-tests about a population mean. You've used a t-table to do t-tests about a population mean. You've used a standard normal table, the z-table, to test hypotheses about population proportions. You've used the chi-square table to test hypotheses about population variances. You've used the F-table to test hypotheses about ratios of variances in the context of comparing the variances of two populations. And you've also used the F-table to perform analysis of variance. So in each of those situations, you have used some kind of a table. In fact, in Module 2, you use the Wilcoxon signed rank table to perform that test. Well, in the same way, we are going to use a table, the Mann-Whitney or the Wilcoxon rank sum table, to perform these tests. Now, I'll just forewarn you, and I think I gave you the same warning when we talked about the Wilcoxon signed rank test, that different resource materials, different textbooks or different reference books, have different formats, different styles of the Mann-Whitney test table. And these different forms of tables exist mainly in their attempts to make the tables more concise so that they don't take up a whole lot of real estate in the appendices. Because for tests like this Mann-Whitney test, because the reference distribution depends on the two sample sizes, the table can get quite voluminous. So it's more than just, like a single standard normal table or a single t-table. There really are different distributions that you have to consider based on the sample sizes. So anyway, that is why different books, they have different table structures. Now, the table structure determines the test statistic that you use and the rejection criteria in terms of how you use or how you evaluate that test statistic. And so we are going to be using a particular table from the same resource that I got the Wilcoxon signed rank table from. And because of that, because we're using that particular table, or let me say it this way, associated with that table is a particular form of the test statistic and a particular type of rejection criteria. So the table that we're using, and really in any situation, regardless of the book you look at, the table that you use is going to dictate the test statistic, the form of the test statistic, and the form of the rejection criteria. Now, in really every hypothesis testing situation we've looked at up to this point, we have classified our hypothesis test as one-tailed tests or two-tailed tests. And if they were one-tailed tests, then we classified them as either right-tailed or left-tailed. In this situation, because the samples and the corresponding populations are labeled according to sample size, Describing one-tailed tests as either left-tailed or right-tailed in general is going to be difficult when presenting the material in a general set of notes because it depends on the labeling and the goals of the analysis. And so therefore what we're going to do as I present this and show you the details of the analysis, we're just going to call both of these types of tests one-tailed tests and then decide which of the tests is to be used in a given context once the samples and populations have been labeled 1 and 2 and having taken into consideration the goals of the analysis. All right, so let's look at the types of hypotheses. So we're going to have what we would call a two-tailed test. The null hypothesis will be that population 1 and population 2 are the same in every way, against the alternative that the two populations differ in terms of location. So again, we might think of this or even speak of it as one population being shifted either to the left or to the right of another. We're not specifying which direction the shift is, we're just saying that there is a shift. All right, the populations differ in terms of location. Using very, very loose notation, and I'm going to be using this for each of the tests that we look at, but keep in mind this is just very, very loosely stated. The null hypothesis could be stated this way: that population 1 is equal to population 2, against the alternative that population 1 is not equal to population 2. And we're keeping in mind that what this really means is that there's a difference in location. Now for the one-tailed test, we're going to have two versions. So I've got the first version of the one-tailed test on this slide. So the null hypothesis here would be that population 1 and population 2 are the same. That's the same null hypothesis as we had for the two-tailed test on the previous slide, against the alternative that population 1 is shifted to the left of population 2. We're saying that there's a difference in location, and we're specifying the direction of population 1 with respect to population 2. Again, using some very, very loose notation, the null hypothesis would be that population 1 is equal to population 2, against the alternative that population 1 is less than or to the left of population 2. All right, so you can see that this is very, very loose notation here, how I'm expressing this. But I think it gets the point across in a succinct way. Okay, the second version of our one-tailed test, the null hypothesis would be the same null hypothesis that population 1 and population 2 are the same. The alternative in this case is that population 1 is shifted to the right of population 2. All right, so again, there's a very specific shift in mind here. It's the idea that population 1 is situated, if you think about a number line with the two distributions on the number line, that population 1 is situated somewhere to the right, maybe a lot to the right, maybe just a little bit to the right of population 2. And again, we're not talking about any particular measure of location, the median, the mean, and so forth. We're just speaking in general terms. Okay, so again, using this very loose notation, the null hypothesis would be that population 1 is equal to population 2. The alternative would be that population 1 is greater than or is situated to the right of the location of population 2. All right, so those are the hypotheses that we can test. We've got the two-tailed test, and then we've got a couple versions of a one-tailed test. And the reason I hesitate in calling these left or right-tailed tests is because we have to wait until we get the labeling, the 1 and 2 labeling. Right? We start off with the A and B labeling, but we've got to wait until we get the labeling for 1 and 2 to specify the hypotheses in this way. And that labeling depends on the sample size. All right, so it just seems to me better to be no more specific than saying version 1 and version 2 on these one-tailed tests. All right, how do we calculate the test statistic? So step 1, we're going to label the samples and populations and notation according to sample size. So again, in general terms, the smaller sample is sample 1, the larger sample is sample 2 with corresponding labeling. Okay, then once we've got the labeling done, then we're going to combine the two samples into one sample, that combined sample, that contains all of the observations in the two samples. Using that combined data set, that combined sample, we're going to create an ascending data array from that combined sample by sorting the observations in that combined sample in ascending order. Once we have that ascending data array, rank the observations by assigning to each observation its position in the ascending data array. The smallest value is assigned rank 1, the largest is assigned rank N1 plus N2. And again, if multiple observations have the same value, then to those tight observations assign as a rank the arithmetic mean of the positions they hold in the ascending data array. Then in step 6, we're going to compute the following value. So we're going to compute the rank sum, the sum of the ranks for sample 1. And then in addition to that, we're going to calculate the conjugate of T1. So T1 prime, and again this is N1, times the quantity N1 plus N2 plus 1 minus T1. Now again, if we've already calculated all of these things, the rank sums and the conjugates for samples A and B, then we don't have to recalculate things, we can just make the association. So then we're going to be using T1, the rank sum for sample 1, and T1 prime, the conjugate of T1, in testing the hypothesis. And depending upon the type of hypothesis, we'll use one or the other of those two values. So how do we use the test statistic to test the hypothesis using small samples? Now, for small samples, the Mann-Whitney reference distribution is provided on Moodle. It looks like a spell check got me there, and can be used to find the appropriate critical point for a given test. Now, the table is labeled A10, and the next two slides show table A10. There are 2 pages for this table. The first slide gives table A10 showing critical points for two-sided tests at the 0.05 level of significance. So the first table is a 0.05 level table, but keep in mind that these critical points are for a two-sided test. Then the second slide gives the critical points for two-sided tests at the 0.01 or the 1% level of significance. Okay, so here is the first table. This is the table of critical points for a two-sided hypothesis test at the 5% level. The way we use the test is to use our sample sizes N1 and N2. We enter the table looking across this row here. We've got sizes for sample 1, values for N1 ranging from 2 up to 15. And then after that we look down this first column. This gives us values for N2, the size of sample 2, which ranges from 4 up to 28. And notice again, remember that N1 is going to be less than or equal to N2 because of the way we did the label. The next table, the next slide, gives us the critical points for a two-sided test at the 1% level. And the structure of the table is exactly the same, the only difference being that, as you can see here, the values are a little bit different. Again, these are critical points for the test. Notice that down here in the footnote to the table, it reminds us that if the groups or samples are unequal in size, then N1 refers to the smaller sample size. So, as I said before, for small samples, the Mann-Whitney reference distribution can be used to find the appropriate critical point for a given test. Now, this is where we need to be careful, and we need to understand the table. We need to understand how to use the table. Because of the way this table is constructed, the critical regions for the 3 kinds of tests that we've talked about, a two-tailed test and then both one-tailed tests, are all specified using left-tailed critical regions. Right? So what that means is that the rejection criterion for each of these 3 tests uses inequalities of the form. We're going to reject the null hypothesis if a test statistic T is less than or equal to C. So it's going to be a left-tail type of test or a left-tailed rejection region, even if we're doing what looks like a right-tailed test. And the reason is because that's how this table has been constructed. So again, the rejection criterion for each of these kinds of tests uses inequalities of the following form. Reject the null hypothesis if T is less than or equal to C, where C is chosen from the table in order for the test to have a specified level of significance. Now, the other thing that I want to point out, the inequality here is non-strict. The reason I want to point this out to you is because if you think back to table A9, the rejection criteria there involved strict inequalities. So for example, T being strictly less than a value C. But in this table, in using this table, we're using non-strict inequalities. So we've got that less than or equal to part there. Now the reason that these 2 tables, even though they come from the same textbook, the reason it's using strict in table A9 and non-strict inequalities in table A10 is because the authors did not create those tables. They got the tables from other resources, journal articles that had different authors, and these tests were developed separately, obviously. And so, for example, in the original resource for table A9 must have used strict inequalities, whereas the author that wrote the paper back in biometrics and created this table, he used non-strict inequalities. So you just need to make a note that in this table, the Mann-Whitney test table, the rejection criteria involve non-strict inequalities. So let's look at the rejection criteria for a two-tailed test. So again, a two-tailed test would be where the null hypothesis says that population 1 and population 2 are the same. Against the alternative, it says that population 1 and population 2 differ in terms of location. The rejection criteria for this test at a significance level of alpha would be to reject the null hypothesis if the test statistic t, which in this case is going to be the minimum of t1 and its conjugate, if that minimum is less than or equal to C sub alpha. And C sub alpha comes from table A10, the Mann-Whitney reference distribution table, and it represents the lower alpha percentage point of that distribution. So this would be the rejection criterion for this two-tailed or two-sided test. Okay, what if we have a one-tailed test, and in particular version 1? Well, again, let's refresh our memories here. The null hypothesis is that population 1 and population 2 are the same, against the alternative that population 1 is shifted to the left of population 2. Then the rejection criteria, again at a significance level of alpha, is to reject the null hypothesis if the test statistic t, now in this case, the test statistic t is just t1, the rank sum for sample 1. So if that is less than or equal to C sub 2 alpha, then we're going to reject the null hypothesis. Now, what is C2 alpha? Now we got to be really careful here. This has the potential to get really confusing. But what that represents is the lower 2 times alpha percentage point of the Mann-Whitney two-sided reference table, table A10. So because the table is giving us critical points for two-sided tests, but this is a one-tailed test, a one-sided test, then we need to be careful. So for example, for a left-tailed test at a significance level of alpha equal to 0.025, then we would go to the 0.05 two-sided table, which is that first table in table A10, and get a critical point from that table. And then finally, the one-tailed test that we're calling version 2. So again, the null hypothesis being that population 1 and population 2 are the same, against the alternative that population 1 is shifted to the right of population 2. So the rejection criteria for that test, again at a significance level of alpha, is to reject the null hypothesis if the test statistic t, which in this case is the conjugate of t1, so t1 prime, if that is less than or equal to C sub 2 alpha. And again, C sub 2 alpha has the same interpretation as on the previous slide. So again, let me just scroll back up. For the two-sided test, for the two-tailed test, the test statistic is going to be the minimum of T1 and the conjugate of T1. For this left-tailed test, the test statistic is T1, and for the right-tailed test, the test statistic T is the conjugate of T1. Okay, that took up a lot of time to describe this test. As you can see, it's fairly involved, and we have to be really careful when we do it. Now, we're going to see how this works. I've got a couple examples that I'm going to show you, but I think to keep the length of this video down as much as possible, I'm going to stop this particular video, and I will start up with the examples on the next video. All right, so we'll see the examples on the other side.